algorithm, enumeration algorithm, and measure the running time as a function of the input size. But there is also another approach. Well, because outputs of enumeration problems is huge, well, we can measure running time as a function of both the input and output size. So if the output is exponential, well, we can take it in account. And then we can look for so-named output polynomial algorithms. These are algorithms whose running time is polynomial in input and output sizes. Well, this algorithm, in fact, could be very bad because, well, if a polynomial is not nice, then, well, the running time could be very huge. Also, well, there is one additional issue with this approach. You can start your enumeration algorithm, and it works for very long time until it starts to output something. It can wait for exponential in the inputs time until it outputs the first solution. It's not nice. That is why the people who are doing enumeration are looking for something better. And here we are coming to so-named polynomial delay algorithms. Here, the algorithm output, here we require that an algorithm should output solution with polynomial in the input delays. What does it mean? So we have input. So the algorithm starts, it works polynomial time, outputs the first solution. Then again, so after polynomial number of steps, it outputs the second solution and so on. And in the end, after it outputs the last solution, it also works for polynomial number of steps and then inform us that it's done. So this is polynomial delay algorithm, and people are really looking for polynomial delay algorithms. Well, in ideal case, you can get linear delay algorithm, or in some cases, you can even get constant delay algorithm, but usually it's amortized time, but we are not going to talk about this yet. Okay, these are enumeration problems, but we are going to do parameterized complexity. Then let us define a parameterized enumeration problem. Well, if we defined an enumeration problem as a tuple, now we defined it as a triple. So L, Sol, and K. Well, the first parts are the same. So L is a decidable language. Sol is a function that computes solutions, or defines solutions. And we have a parameterization. Here, well, it's defined as a function of the input. But, well, we can assume that it's just given together with each input, as usual in parameterized complexity. Okay, this is the definition of parameterized problem, and then we can consider parameterized enumeration algorithms. We are interested in two types of algorithms, FPT algorithms. If the problem is nice, then we can hope to enumerate everything, all solution in FPT time, in usual way. But it's not always the case. But sometimes we can do FPT delays. FPT delay algorithm defined in the same way as polynomial delay algorithm, but now we allow delays to be FPT in the parameter. Okay, now we have background in parameterized enumeration problems. Let us move further and let us move to kernels. Well, really, enumeration kernels were known for some time. In particular, such kernels were introduced by Damashke and Seymer and Zeider. I'm not going to talk a lot about these kernels, but let me just say that the main idea was to compress instance of a parameterized enumeration problem to a small instance whose size is bounded by a function of parameter in such a way that this compression instance would keep all the solutions. Just to give you an example, if you say aim to list all minimal vertex cover of size at most k, where a k is a parameter. You can do this job while using the very basic Bose kernels. You can do it as an exercise. Okay, this is nice, but unfortunately, it's not. It's not very common for a problem to have such a kernel. The reason is that we need the following properties. The number of solutions should be bounded by some function of parameter. Otherwise, we cannot hope to compress everything to small instance that that represents all the solutions. So we would like to do something else. And this was done by Clignot, Meyer, Müller, Schmidt, and Vollmer. They introduced so-named enum kernels. We are going to exploit their approach, but with one important correction that I'm going to mention a bit further. But now let us move to the definitions. So we have a parameterized enumeration problem, and we are going to define two types of kernels for such a problem. One kernels somehow tailored for a problem that can be solved in FPT time, and the second kernel is going to be introduced for problems that admit polynomial delay, FPT delay enumeration algorithms. But let us start with this with a simple definition of enumeration kernels. If you know lossy kernels, well, you would see something familiar because we borrowed some notions from this area. So enumeration kernelization or enumeration kernel for pi is a pair of algorithms, A and A prime, with the following properties. First, what A is doing, it does the following job. For every instance of our problem, it computes in polynomial in the input and parameter size an new instance of the same enumeration problem that has bounded size, bounded by some computable function. And second, this is about A prime. Well, A prime does solution lifting. So for every solution, for the compressed instance Y, for every solution S for the compressed instance Y, so A prime computes in polynomial in the input kernel size and parameter size time, a non-empty set of solution for the original problem, for the original instance, such that computed solutions for all instances, for all solutions for Y, form a partition of the set of solution of X. So again, so what we are doing? So by the algorithm A, we compress instance in a very usual way. So, but A prime is used to go back. So we have kernel, small instance, we solve it, take every solution, and from this solution, taking access to the input. So we can compute a set of solutions for the original instance in a polynomial time. And if we go over all solutions for the kernel, then we would be able to obtain solution all the solutions for the original input, for the original instance. Okay, this is enumeration kernel. This kernel is tailored for problems that can be solved in FPT time. Now, let me just observe that as it's standard, we say that F is the size of kernel, A is kernelization algorithm, and A prime is a solution lifting algorithm. Now, let me give the second definition. A delay enumeration kernelization for pi is defined in similar way, but it's again the pair of algorithm A and A prime with the following properties. Well, the first property for A is the same, exactly the same. So we compress the original instance to a small instance, or instance of bounded size. But A prime is doing a slightly different job. So So A prime given a solution S for the compressed instance, it computes this polynomial delay non-empty set of solutions. And again, if we go over all solutions for the compressed instance, then we would be able to list all the solutions for the original instance. So the difference now that A prime is polynomial delay algorithms, not just polynomial algorithm. Well, if it's clear, then it would be easy for you to see that every enumeration kernel is delay enumeration kernel. Well, let me now mention what is the difference between our definition and the definition given by Crendieu et al. Well, the difference is in the second condition. So Crendieu et al. Required A to be a FPT delay algorithm. But it's not nice because it would imply that if a problem admits a kernel at all, a delay kernel, delay enumeration kernel, it has delay enumeration of constant size. So the right way to define kernel, by our opinion, is to define as we did it and require A prime to be a polynomial delay algorithm. So we have this definition. Well, and we believe that this approach is useful. So it's a very traditional kernelization type approach. So we have a solution. We have a hard problem. We have problem. We compress it to a hard core, and if we're able to compute solutions for this hard core small instance, then we're able to go back by more or less easy algorithm, polynomial algorithm. It's either just polynomial algorithm or polynomial delay algorithm. So that is why, well, we believe that this approach, this kernelization approach could be interesting, but there is one more thing that I would like to mention. Well, there is one issue with enumeration problems. Well, as I mentioned, it's typical that the number of solutions is very huge, it's exponential. But then even if you have exponential algorithm, well, this enumeration algorithm, at least of this exponential number of solutions, what are you going to do with all the solutions? Well, you are just going to get too many of them. But maybe not all the problems, all the solutions are interesting. And to work as a step to make our aim more easy, Mike Failovs and et al. Introduces the concepts of diverse solutions. So if we have enumeration problems, we would like to get solutions that somehow far away, very different from each other. They considered very rarely Hamming distance between solutions. But here, with these kernelizations, we can argue somehow that a kernel gives us structurally diverse solutions. So you see, what is going to happen? So we have instance, so we compress it, and then we obtain hard core. This hard core has bounded size, it has bounded number of solutions. And the solutions are hard to find. And somehow this implies that the solutions should be structurally different. But then, given these different solutions, we can use some nice and easy polynomial, say polynomial delay algorithm to generate other solutions of the same type if we are interested in that. Okay, this one more arguments to consider enumeration kernels. But now let us convince you that these kernels behave well similarly to classical kernels, but simultaneously I would like to point differences. And for this, I'm going to prove the following theorem. A parameterized enumeration problem can be solved by an FPT enumeration algorithm or an FPT delay algorithm, respectively, if and only if this problem admits enumeration kernels or delay enumeration kernel respectively. So it's very similar to classical result about FPT algorithm and classical kernels. And let me just observe further that a problem can be solved in polynomial time or with polynomial delay if and only if it admits a kernel of constant size. So indeed, we have this nice correspondence. Okay, let me show this theorem, and you are going to see the difference between classical kernels and enumeration kernels. And I'm going to show the first part.
Peter?
Yep.
Yeah, I think Diptopri wants to ask something.
Yeah, so Peter, can you please go back to the previous slide? Just I have one minor thing to just know. So here is this thing. So look at the reduced instance y. Now, yes. Say you are given a solution to the reduced instance. Say, how about the size of the solution of the reduced instance, and then use this solution S of the reduced instance, then the solution you are going to compute for the original instance. How about the size of these solutions are related? Should they be somehow equivalent to the, for example, for feedback vertex set problem?
No, well, we don't require it, but observe what we discussed in the beginning. So solution is computal function. So is computal function. So if y has bounded size, then the solution also all solutions have bounded size, and the number of solution is bounded by a function of the parameter. Now.
Okay.
So it's it cannot happen that y is very huge and or solution for y is S is very huge.
Okay.
Everything is bounded by parameter.
Okay.
Did I answer your question?
Yes.
Okay, thank you for the question. So, and let us go further and let us return to this theorem. So I'm going to show you the first slide, and let me show for, say, FPT delay algorithms. So in one direction, it's easy. If we have kernel, then we have FPT delay enumeration algorithm. And I say thank you for the question, just because it helps, well, this question helps to see why this is the case. So, well, we have compressed instance. It has bounded by a function parameter size. Sol is computable function. So all the solutions, well, the number of solutions is bounded now a function of parameter, and every solution has a size that is bounded by a function of parameter. And then we just given, we can list all the solutions for Y constructed instance in time that is a function of the parameter. And then if we have a polynomial solution lifting algorithm, we can return to the original instance. So this how this theorem is proved in one direction. The interesting part is, of course, is the second, the opposite direction. And let me give you incorrect proof. Please watch my hands, and maybe you can say what is wrong with the proof. Well, assume that our problem pi can be solved with FPT delay f of k times input size to the c, so wherever c is some constant. Well, let us introduce trivial yes and no instances. We say that instance y is a trivial no instance if is an instance of minimum size with empty set of solution. And we say that y is a trivial yes instance if is a yes instance is an instance with minimum size of the set of solution that subject to this condition has minimum size. Observe that if a problem has no instances, then a trivial no instance has a constant size. And if our problem has yes instances, trivial yes instance has constant size. Okay, now what we do? We just try to follow the same scheme as, well, a classical result. Well, really, we are doing it not right way, but okay. So we just check whether the input size is at least the function of the parameter. Well, if it holds, then we have this nice property that our algorithm is really polynomial delay algorithm. If x is big, then our algorithm runs in time x to the size of x to the c plus 1. And then what we do? Then our kernelization algorithm is going to output either trivial or no instance. How? Well, we can do the following trick. So we just have our instance, original instance. We have polynomial delay algorithm now, and we can use this polynomial delay algorithm to verify whether we have yes or no instance. If it's a yes instance, we output a trivial yes instance. Or if it's no instance, so we have no solution, we output a trivial no instance. And how we go construct our solution lifting algorithms? If we have a yes instance constructed by our kernelization, when this instance has a constant size, we list all its solution in constant time and somehow order them. Then what we do? Then our solution algorithm for, say, is solution of y outputs the if solution of x produced by the enumeration algorithm. We again can run our polynomial delay enumeration algorithm. Then we just count how many solutions we output, and then we just got and we output the solution with the required number. So this is done for the first instances. But then for the last, for the first solutions of the kernel, but for the last solution, we just output all remaining solution for the input instance with polynomial delay. This is how solution lifting algorithm behave for no instance, for yes instances. For no instance, of course, it outputs nothing, so it's not a problem. Okay, this is done if x, the size of x, is at least f of k. Otherwise, well, then, well, we just output the original instance because, well, because the size is bounded by a function of the parameter. So done. Okay, so the size of kernel is f of k. So, well, if for offline presentation, I would stop and ask what's wrong with this arguments. I don't know whether someone can say it. Can see
So
it.
what if like finding any solution is NP hard, right?
No, it's not a problem. Well, if you find any solution, just find one solution is already hard, then we have no FPT enumeration algorithm. FPT delay. And we assume that, well, we have FPT enumeration algorithm, FPT delay enumeration algorithm. We can solve our problem. Well, the issue is, of course, well, there are two holes really. And one hole in this arguments really is similar to the classical case. Well, here we verify whether the input size x is at least f of k. But computing f of k could be hard. So, well, it's computer function, so we can do it, but it can demand time that is exponential the f of k. Well, for classical kernels, to go around this issue, well, people just run FPT algorithm in time in the input size C+1 steps. And if this algorithm outputs solution, if it says that we have yes instance, we are happy, we solve our problem in polynomial time. Otherwise, if it does not, then we know that f of k is big. So we know it without computing f of k. But we cannot do it for enumeration. The issue is that, well, we have now delay algorithm. And if we run this delay algorithm for, say, the size of x to the c+1 steps, and it starts to output something, it does not say us anything about future delays. Maybe the further delays are bigger, and then f is bigger. So, and this is a difference. And to go around this issue, we have to recall that f is a computable function. It means that there is an algorithm that computes f of k, and this algorithm runs in, say, time g of k. What we do? So we run this algorithm for the size of x steps to compute f of k. And what are the possible outputs? So it can happen that this output would output f of k. Then we are happy, we solve the problem, so and we have the value f of k that we can use. And we did it in polynomial time, so fine. But it can happen that we stop. So, but if f of a fails to compute f of k in the first, the size of x steps, then we can conclude that g of k is big. Not f, but g. But who cares? Then we just return the input instance. We still obtain kernel, but now the kernel size is h of k, where h is a maximum of f of k and g of k. But still we have kernel. So as you see, we have to, we still we have the same issue. We can go around, but we do it in a different way if you compare with standard proof equivalence of existence of FPT algorithm and kernel. It's an FPT algorithm in existence of kernel. Sorry. Okay, but this was just the first whole. So we have another one. So and we are going to sometimes we are going to output trivial yes and no instances. But to output them, we have to compute them. If to compute if our problem has trivial no instances, it's not a problem to compute a no instance, a trivial no instance. We do it just brute force. So what we do, we just start to list all strings of length 1, 2, so on and so on, until we get a string that gives us no instance. And we know that it should be a constant. That depends on only on the problem. It's fine. So, but we cannot do this trick with yes instances. Well, we can try to repeat this brute force argument and start listing all strings and verify whether they have solutions. But how to verify that the number of solutions is minimum? So if we get some instance with 10 solutions, well, it can happen that somewhere in future we are going to get an instance with 9 instances, and we don't know when to stop. So brute force does not help. So fortunately for us, we don't need to do this. So well, we can compute an instance Z of minimum size such the number of solutions for Z is at most the number of solutions for the original instance. So how to do this? So we just do brute force. If we can verify by our algorithm, enumeration algorithm, whether the solution of X is non-empty, then we try in brute force, we do brute force scheme and find an instance of minimum size such that the solution, the set of solutions for Z is non-empty. And then we again check using our enumeration algorithm, that in this case is a polynomial delay algorithm, whether we have the number of solution of Z is at most the number of solution of X. we just run our enumeration algorithm for x. And because the number of solution of z is constant, we can verify this inequality. Well, if we get it, we just return z. But if not, then we know that somewhere exists a solution of constant size. Of course, size, we have an instance of constant size z such that the number of solution is at most the number of solution of x. And again, we can use brute force. So we can find a solution, find an instance with the number of solution at most the number of solution for the original instance, and then we can use it for solution lifting. Okay, so you can see that it's from one side, it's very similar to the classical proof that a parameterized problem admits an FPT algorithm if and only if it admits a kernel. But from the other side, it's a bit different. It's the proof now is more involved. In particular, here we have even issues with trivial yes instances. Okay, these are kernels, and now let us go to an example. Maybe we would not be able to go into details, but let me just try to explain at least something. Let us consider matching cut problems. Suppose we have a graph G, and the cut is a partition of the vertex set, and we say that the set of edges between two parts is an edge cut. And a matching cut is a possible empty edge set being an edge cut and matching. So something like this. So we have two parts and we have matching between them. It should be a cut. And let me underline that we always defined matching cut as a set of edges, not a partition of the set of vertices. It's important if our graph is disconnected. For example, if our graph has no edges at all, so but say n vertices, then because empty set is a matching cut, we have really 2 to the n possible partition of the set of vertices, but we just have one empty matching cut. Okay, this definition of matching cut that we use, and we consider the following problems. So enum MC, enumerate all matching cuts of a given graph. Well, we also can try to enumerate all inclusion minimal matching cuts. This is another problem. And if we consider minimal, well, we can also consider maximal matching cuts. And for the last problem, the task is to enumerate all inclusion maximal matching cuts. What can we say about these problems? And it's known that it's already NP-complete to decide whether a graph has a matching cut. It was proved by Hvatal. And this implies that all these problems cannot be solved in output polynomial time unless P equals NP. If it's already hard to decide whether we have one solution, then it's hard to enumerate. So it makes sense to consider parameterized complexity techniques to deal with this problem, and let us try structural parameterizations. And we can observe that all these problems admit FPT delay algorithm when parameterized by the tree width or click width of the input graph. This really follows from the result of Carcel for enumeration problems that generalize the known result for the results that probably you know about graphs of bounded trees, but for decision problems or optimization problems. We also can do the same tricks for enumeration problems, and this was proved by Carcel. We can express all these problems in monadic second-order logic, and then we can do enumeration. Okay. But also we can observe that the decision variant of the problem does not admit a polynomial kernel for tree-width or click-width parameterizations unless NP is subset of CoNP/poly. This was observed by Kamashevich, Krach, and Le in their recent paper. It's a really easy observation. If you know cross-composition techniques, then you can deconstruct them. But what is important for us, that this implies that all these problems do not admit polynomial delay kernels, unless, well, this condition that NP, unless we get that NP is subset of CoNP/poly. So no hope for tree-width parameterization. Okay, so let us try the standard trick and go for stronger parameterization. What about vertex cover parameterization? And now we can make some observations that somehow show that our kernels could be useful. Well, let us first look at minimal matching cuts and consider star K1n. Well, a star with n leaves, of course, has n matching cuts. Just every edge composes a matching cut. Well, feedback vertex set is, of course, 1. Vertex cover number is, of course, 1. And the number of cuts, matching cuts, cannot be bounded by a number of solutions. So we cannot get, say, kernels of the stars that were considered by Damashke and Seymour and Zeider. So we cannot get full kernels. But we can get really enumeration kernels. Now let us consider maximal matching cuts or just just matching cuts. Now let us consider unions of stars. So we have union of k stars with the same number of vertices, and we can observe that now vertex cover number is k, and this graph has n over k to the k matching cuts. Well, we just can pick one edge from each star or pick nothing. This way you obtain all all matching cuts. And if we pick exactly one edge from each star, we get maximal matching cuts. You know that the number of these cuts is big. It's not, the number is not bounded by a function of k times poly n. So we cannot hope for FPT enumeration algorithm, of course, because the number of enumerating object is very huge, but we also cannot hope for enumeration kernels. And this is this follows just from this observation that the number of objects could be very huge. But still, we can get delay enumeration kernels. And let me briefly explain in the remaining, say, 5-10 minutes how to do it. Just to make the life easier, let us construct kernel for the decision problem. So here we want to decide whether a graph has any matching cut, and we parameterize this problem by vertex cover number. Suppose that we have a graph with a vertex cover number at most k. Well, if it's disconnected, then empty set is minimum, is unique, minimal maximum matching cut. And of course, we have matching cut, so we return empty set. And if it has a bridge, it's connected a bridge, then we again have matching cut. Then we can return the corresponding trivial yes instances. So we can solve problem directly. Suppose now that now our graph is connected and it has no bridges. Then we compute some vertex cover. We use standard approximation, so we just compute any inclusion maximal matching and take its end vertices, it gives us vertex cover of size at most 2k. We have vertex cover and its complement independent set. And then we do the following marking. It's going to be explained later on a picture, but what we do. So we consider pairs of distinct vertices in computed vertex cover. And for each pair, we just look at the neighborhood in the independent set. And we take, well, 3 common neighbors, or less if we have less than 3 common neighbors. We mark them. And that's essentially all the construction, because now we delete all the unmarked vertices of I and return the obtained instance. So this way we obtain a graph with O of k square vertices. We have at most 2k vertices in vertex cover. And for every 2 vertices in X, we mark it at most 3 common neighbors. So this is shown here. So this is a crucial step. Our marking for every 2 vertices of X, we mark 3 vertices in independent set. What is important? And what is important is that if we have such an object, 2 blue vertices and 3 common red neighbors, then we cannot separate them by any matching cut. Moreover, if we have more common neighbors of these 2 blue vertices, then we also cannot separate them. We can try to separate by cut 2 blue vertices as it's shown here. But then at least one of these blue vertices has 2 common incident red edges that I cut. And this wrong, it's not a matching. So it cannot happen. And we cannot cut our graph like this. Now we have red vertex that sees 2 edges across the cut. Then we show that we obtain that the set of edges is a matching cut of G if and only if M is a matching cut of H. So H is indeed this kernel, so it has a matching cut if and only if G has a matching cut. Quite easy, but it's not an enumeration kernel. It does not work. So just because, well, so we throw away many interesting things like bridges. The case, well, we exclude from consideration the case when we have bridges, and the case, well, we ignore the case when our graph is disconnected. We cannot do these things if we are dealing with enumeration problems. So we have to do something more sophisticated, but really in this case, it's not so difficult. And the construction of enumeration kernels is shown here. So we have a graph with a vertex cover of at most k. Now we start with approximation. We compute approximation for vertex cover. Now, if I contains an isolated vertex, then we pick one of these vertices and mark it. It helps us to keep information that our graph is disconnected. And then, because we cannot forget about bridges, we keep them, but we keep information not about all of them, but just some pendant bridges. For this, for every vertex in independent set, if in the vertex cover X, if we have a neighbor in independent set of degree 1, we just mark one of such neighbors. And then we repeat the old marking step for pairs of vertices of X. This is all the construction. So then again, we delete all unmarked vertices of I and return the obtained graph H. So we get kernel and it still has quadratic size. So it's shown here. So we just now do something more complicated. We still have X. If we have an isolated vertex in independent set, we mark it. So it's here. So now we are looking to pendant neighbors of vertices of X. And again, we mark one of these neighbors, as it's shown here downstairs. and upstairs we do this marking for pairs of vertices. And how now we do enumeration? So let me show at least for minimal matching cuts. Let us observe that G is connected if and only if H is connected. And how we do lifting if H is disconnected. So if H has empty set as a matching cut, then we just output this empty set for the original graph. And this is unique minimal matching cut. We are done. So now if our graph is connected, then it can happen that a matching cut in G contains an H incident to a vertex of degree 1 in the independent set. But then, by minimality, it's unique H of matching cut, minimal matching cut. But then our kernel has a similar H. So because we marked one pendant neighbor. And now we can easily construct solution lifting algorithm. Well, let me just show using this picture. So if we have matching cut in H composed by this session red H that join a vertex cover with a vertex of independent set. Then to list all matching cut correspond the original graphs corresponding to this cut. So we just look at these green edges and list them one by one. And this way we list all matching cuts that correspond to the matching cut of the kernel. And finally, if we have a matching cut of H that does not contain the pendant edges, then it should be a matching cut in this upper part. And these matching cuts correspond to matching cuts of the original graph. Then for each matching cut of this type, we just lift, our solution lifting algorithm just outputs it. So we still can do it. And then we show the following theorem. Enumeration minimal matching cuts admits enumeration kernel with quadratic number of vertices. Observe that the number of minimal matching cuts is not bounded by the function of parameter, but still we have enumeration kernel of quadratic size. Well, this is for minimal matching cuts, but we can do something similar for all matching cuts or maximal matching cuts. But now things are a bit more complicated because it can happen that our solution for the original graph G contains several edges that are incident to vertices of degree 1 in the independent set. But then what is going to happen? So really, then we can again define, we call them equivalent solutions composed by similar edges in kernel. So for example, if a solution contains this green edge, we have a solution that contains this blue edge in the kernel. Again, for this green edge in solution, we have this blue edge in the kernel. And we can use this property to go back. And this way we obtain a delay enumeration kernel again of quadratic size. Observe that now we have delay enumeration kernel, but not enumeration kernel. It's impossible. It's unconditional claim. And again, so we can have a lot of solutions. So the number of solutions is huge. It's not FPT in the parameter, but still we have enumeration. Well, maybe this last part was not precise because I started to hurry, but I hope you at least you got at least some flavor of our approach. So let me conclude. Well, we consider the concept of enumeration or delay enumeration kernelization. We hope that this concept is interesting and may lead to nice results. We obtained kernels for enumeration matching cut problems parameterized by the vertex cover number. In fact, in our paper, we consider more interesting parameterization by the neighborhood diversity, modular width. In the most interesting cases, parameterized by cyclomatic number or feedback age number. And what are interesting open problems? Well, if we ask about something about matching cuts, what about parameterization by the feedback vertex number? We don't know really. Really, the case of feedback age number is already very messy. We managed to go through it, but we got stuck with the feedback vertex number, but still it could be doable. But of course, more interesting is the second question. Are some other nice enumeration or delay enumeration kernels for other parameterized enumeration problems? Or maybe we can show, say, FPT algorithm, but lower bounds. So, and hope that I got at least some of you interested in this enumeration problems and kernelization enumeration problems. So thank you for attention. I am ready to answer questions. Now I see that there are some questions in chat.
There was some discussion which has been resolved, I think. And yeah, thank you for the great talk. And yes, we are open for questions now. If anybody has questions, they can unmute and ask right away. Or if you prefer, you can type in the chat.
Hi, Peter.
Yeah.
Yeah, so you showed that there is no polynomial delay kernel for enumeration matching cut when parameterized by tree width. But is there a FPT delay algorithm? Like, is the problem FPT when parameterized by tree width or click width?
Yes, you have FPT delay enumeration algorithm. It follows from the result of Corsair. So you can express this problem express properties that a set of edges is a matching cut in monadic second order logic. And then this automatically implies, the result of Corsair automatically implies that you have FPT delay algorithm when we parameterize by tree widths or click widths.
Yeah, okay, thanks.
Well, really for click width, sorry, I say it's a wrong thing. So you have to express, using MSO1, so you can quantify only over vertices and set of vertices, but you can do it. So
Okay.
click width is also holds.
Okay.
Okay, I guess no more questions then. All right then, thank you once again for the great talk. It was very nice to have you. And thanks to the audience for being around. So we conclude the session here for today and see you all next week. Bye.
Thank you, bye.